My name is Dara Hanley from Team Dara, and I'm a AI researcher at Doubleyard. I am going to explain the third place solution to the 2022 challenge from RSNA on cervical spine fracture detection. So the pipeline, we have four main stages. The first is to generate bounding boxes from the DICOM slices for each of the C1 to C7 vertebrae. We actually do this at slice level, generate these bounding boxes and aggregate them to the DICOM level. Next stage is to create slice level vertebrae ratio labels using segmentations. We'll explain this in a bit more detail later and predict them for the full data set. So we have these slice level labels at, we have them at slice level. And we use the vertebrae ratio labels to make fracture labels, because we have the fracture labels at study level. So once we know where the vertebrae are, we can multiply these through and get slice level fracture labels. Again, we'll explain this more in detail. Once we have these labels at slice level, we're going to train a model to learn slice-wise vertebrae and fracture labels. This will run for a long time, and then we're going to take the weights of this model and load the CNN backbone weights into a new model with the same architecture, slightly different output, and train a new model to learn the study level vertebrae fractures. So we only have 2,000 of those, so this one won't run as long. A little bit to talk about these slice level labels that we use as an intermediate sort of training guidance. I'm going to talk about how they work quickly. So let's say we have a DICOM and these are two slices. This slice denotes, for example, we'd say this is the C1 segmentation. And we'd say this is if this is the slice with the largest amount of pixels segmented for the C1 vertebrae, that would be sort of our anchoring max pixel count for C1, and we say that 6,500 pixels is segmented for that. So the max C1 segmentation size we have is 6,500 samples. Then what we do is we go through all the other slices and say, okay, how many C1 segmentation pixels are there? Let's say in this one we have 1,800. What we do is we divide the 1,800 by the 6,500, which is the max amount we have for C1, and we get as a vertebrae label for this 0.27692. So the idea of this vertebrae label, this ratio label, is it's sort of what percentage of the vertebrae do we see in each slice. So the vertebrae label for this would be 1, because it's be 6,500 divided by 6,500. So what we do is we have that for the segmentations. For the studies where we have segmentations, so we train a model on the studies where we have segmentations, and then predict on all the other studies, and get the vertebrae labels for those. If we were to put this on sort of a 2D plane, or a 1D plane, I'd say this is what it would look like if we say slice number is the x-axis and this ratio label is the y-axis. You can see here each of the vertebrae and the ratio of vertebrae you see, and you see we start with the C1, then we go on to the C2 and so on. So these are the slice numbers here, and to get we can then get the fracture labels just by taking the study level fracture label for each vertebrae and we multiply it through. So in this case only C5, C6 and C7 have fractures, so the rest of them we say we have 0 fractures in the rest of them, but for example slice 150 would have 0.2 of C5, so we'd put the fracture label at 0.2, and this slice maybe 140 or something would have 0.8, if that makes sense. So we just multiply through the study level fractures by the slice level fractures. Just one comment on this. If it did make it easier for annotators just to sort of roughly label up in each slice how much of each vertebrae we see. So instead of creating a segmentation map, just put in a rough ratio of what percentage of the vertebrae is seen in each slice. Then that could be used as a label if that was easier to create than segmentations. That could be used, and I think this could be a way that you could scale up and label things quicker than actually going into each slice and creating a segmentation map. We also don't use the fracture bounding boxes at all in the study. So the only thing we'd need is sort of information like this: each slice, what ratio of the segment of each vertebrae do we see? And we could learn based on that and the higher level fracture information that we got in train.csv. So to look at the code, there's this sort of breaks down the GitHub. If you look into the GitHub, you'll see different folders and different files. The way we've done it is each stage in the process we have a different script that you can run to run that stage of the process. It does some pre-processing, post-processing, and also some training of models. This is the models stored. So each of these is models stored in or that need to be run. And each of the models has a config file. So if you go into configs, you see the config file, the parameters of the model that are run. And this is the backbones. Sometimes in the configs you'd see a test. What that means is this is trained, let's say, where we have segmentation. This is the training config where we have segmentations and we learn bounding boxes, for example, and then when we want to predict on all the data, we take this second config, which predicts over all the data. These are basically the same thing, only that this picks up all the data and runs inference based on the model weights seen here. So yeah, the backbones, what you can see here is this first script is to download the data, second script to create the bounding boxes for the data. Third script is to get slice level vertebrae labels, as we just explained. The next script trains on the slice level fractures and study level fractures. In each config, we'd point to a data pre-processing script, which can be seen under the data folder, and the associated script you should be looking at that's associated with the config. It's also in the config file, but just I laid it out in a table just to make it easier and make sure everything is in there. That would be the name of it. So dsloc dh1a.py, and then the model code would be seen in the models folder, and you should be looking at these scripts for these configs, and there's post-processing as well. We don't do post-processing for the last 4 processes. So if you go in, this should explain out a bit in detail how the process is run, but it's all in the README of the GitHub. You can see how to navigate in there as well. So to talk about the stages, we talked a little bit about how we get the slice level ratio. Oh, sorry, this is the bounding boxes. So what we do, we crop out bounding boxes for each of, to make it easier to give more resolution on the DICOM. Again, what we do is we get a higher level bounding box for each of the studies, but given that we had the segmentation maps on slice level, we train our model based on the bounding box around the segmentation map. So for example, this could be the C1 segmentation, and we just place a box around that, and that's what this first model learns. We don't make a separate box for different vertebrae. So if there's C1 and C2 are in the same slice, we put a box around both of them, and the model doesn't have to learn, this is a C1 part, this is a C2 part. It just learns what's a C1 to 7 bounding box for that slice. Then what we do is we predict all the we train where we have segmentation maps, and we predict it out for all the other data where we don't have segmentation maps. And then, as mentioned, we aggregate up to the how would I say, the smallest box that you can get that fits around all vertebrae in the study. So what we want to do is crop out a part of the slice, a part of the study where we'll capture all the C1 to 7 vertebrae in one go. So we don't have separate, when we're doing pre-processing and training later, we don't have a separate box for each slice. We just have one box per study, and that's what you can see here. One box per study here, and that's got by aggregating up these slice level boxes. What we also do is, and it's explained in the README, we give a probability that there is that C1 to 7 vertebra in each slice. And what we've done here is said, okay, in this study, there was a very high probability that before slice 47, there was no vertebrae. And after slice 203, there's no vertebrae. So no C1 to 7 vertebrae. And what we do in the final stage of training and for inference is we ignore the slices before that period and after that period, because it's just giving noise to the model. The model really needs to learn and infer on the part where there is vertebrae, especially since it's a sequential model. The more you can take out data, irrelevant data, the better the model will perform. So we get this range of where we say there's a high probability that there's nothing before this point or after this point for each of the studies, and crop that out. The architecture, how it works in all the following models. So after we calculate out our bounding boxes, it's sort of the same base architecture with a couple of different changes each time. So as mentioned, we have one aggregated box, and we crop out the portion of the DICOM that'll contain all the vertebrae. we take all those cropped slices. In model 2 and 3, I'll just move on here. In model 2 and 3, what we do, we're initially training the model, and what we do is we have our ratio labels that we want to learn and train on, and we take random slices out of, so z-axis slices out of the DICOM. Those random slices are fixed at 96, so it's 96 slices, so it's 2.5D images that we make. We take 3 slices per image, so if we take 96 slices, we divide that by 3, and it gives us 32 images that actually goes into the model for this sequence. We pass that through a CNN, take the gap layer for each of those 32. We stack up the sequence of the 32 gap layers that we took from the CNN. Then we pass those through a bi-LSTM and a dense block and a tension. And then for model 2, we learn where's the vertebrae which vertebrae is it along here. So those vertebrae ratio labels we learn first. In the next stage of modeling, what we do is we take those vertebrae labels that we learned and put in the vertebrae and the fracture labels. And model 3, again, we slice out along the z-axis and learn for each slice or each 2.5D image what's the vertebrae ratio and the fracture ratio for each of those slices. And then again the same architecture for stage 4, except we take the weights of stage 3 and load it into stage 4, and we fine tune on the study level. So on stage 4, we don't take a random 96 slice crop from the z-axis. We take the whole study, the sequence of slices in the whole study, and we learn the final fracture labels. But again, it's taken from the frozen weights. So we take the CNN frozen weights from stage 3, where we were learning slice level, and we load that into stage 4, where we're learning study level labels. So to go through again in a bit more detail each one of those. So stage 2, we want to learn those slice level vertebrae training on the segmentation label data. So again, just going back here, what we're doing here is we've created these labels for the segmentation maps, and we want to make a model to learn to be able to create those vertebrae labels for all the data. And that's what that stage 2 is doing. So 32 by 3D, 96 slices along the z-axis. We crop out the box, resize it to 512 by 512, pass it through the gap layer. The label is the rate of pixel count for a vertebrae in the slice. So that ratio that we talked through. RMSE losses used, and yes, again we use this model going forward as well, but this is just to learn that. So as a final step, when we predict on all the data, we have these vertebrae ratio predictions, and as mentioned before, we multiply these by the study. I need to update this to the study level fracture labels to give slice level fracture labels. Vertebrae study level fracture labels to give slice level fracture labels. So at this stage, what we've learned is for all the data we have vertebrae slice ratio predictions. So for each slice, what ratio of the vertebrae is in there, and we also have is that vertebrae fractured or not? A ratio number is that vertebrae fractured or not. So we take that data that we've predicted and we train a second model where we, again, those 32 by 3D 96 slices along the z-axis, we randomly take them out of different studies, crop out the image again, resize to 512, extract the gap layer, pass into the CNN. We take those labels from stage 2 that we talked through, and the model uses that, and we use RMSE loss to learn the vertebrae and fracture labels on all the data. This runs very long. It runs about 10 hours on a 40 gig GPU card. So because there's a lot of data to work through, we're taking a lot of different overlapping slices of those 96 slices. So we've got a pretty strong model at this stage which is able to pick up which vertebrae it sees and if it's fractured or not, the chance that it's fractured or not. And what we do in the next stage is we take the previous stage's CNN, we load that in here to this model, and we initialize a new LSTM and a tension layer, and we learn on the study level fractures for each vertebrae, as well as if there's a fracture at all in the study. We don't take random crops out here, we just take the whole study where we have vertebrae. So you remember earlier we talked about the bounding boxes. We're able to sort of say, okay, this is where the vertebrae bounding boxes start, this is where they end. So we take that portion of it, we pass in here, extract the gap layer and pass it through and learn those study level labels. This model runs for about an hour, and the loss on this is just the loss, the metric that was given for the competition. So I think we're at the end now. So thank you very much for hosting the competition. I really enjoyed it again, and it's always a challenge, and to see how we can approach these problems. And I hope RSNA, ASSR and ASNR teams will be back next year to give us another challenge. We'd really look forward to that. Thank you.